Hi, my name is Ethan Nowaska, and this is the Week 2 Explainer video looking at problem 66 in chapter 14. Air flows through the tube shown below at a rate of 1200 centimeters cubed per second. Assume that air is an ideal fluid, meaning it has no resistance running against it. What is the height h of mercury in the right side of the U tube? So what we're looking for is this height. As we can see that this side is higher raised than this side, and we don't want to know how much higher. In the diagram, we can see that this part of the tube is larger at 2 centimeters diameter, and this part of the tube is smaller at 4 millimeters diameter. And we have our givens here, denoted as Q for the rate of flow, which is what they use in the book, and will become apparent in the equation of continuity. Diameter of tube 1, diameter of tube 2. And then we want to find the height the mercury is raised. And then we're going to use the equation of continuity to find different velocities. Then we're going to use Bernoulli's equation to find air pressure, and then we're going to convert that air pressure to find pressure difference for the mercury. And that's how we're going to solve this problem. So we're going to first look at the equation of continuity, and this equation just explains that flow is faster in narrower parts of a tube and slower in larger parts of a tube. But it is the same rate of flow, or Q, throughout. And this is very nice because we can solve for our area 1 and our area 2 using our diameters, which is d1 divided by 2 squared times pi, and d2 divided by 2 squared times pi. And we get these values converted into meters squared right here. And we can then solve for, now knowing our areas, our area 1 and area 2, we can solve for our velocities because we know the Q. We just convert our Q into meters instead of centimeters. And we can divide our Q divided by our A to get our V. And so for V1, we get 3.82 meters per second. And then for V2, we get 95.54 meters per second. And we're going to use these two values to plug into our Bernoulli's equation. Now, when we look at Bernoulli's equation, this is a very important part of fluid dynamics, and it describes the relationship between energy, work, and the pressure. And so we can know this by what it's made up of, which is our kinetic energy in fluid, our potential energy gravitationally in fluid, and then our work in fluid. And if you just add these all together, you literally get Bernoulli's equation, divide out the volumes because everything has a volume. And you get this very nice modified version of Bernoulli's equation, which reads out as 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho gy2 minus rho gy1 is equal to p1 minus p2. Now you want to be very careful here because you have this rho and this p, and while they look very similar, they're very different in what they mean. P is the pressure, rho is the fluid density, and you don't want to get these two mixed up. So using this Bernoulli's equation, we are going to set that part up. Now, when we look at our Bernoulli's equation, we can note that because this is a pipe on a horizontal axis, the y2 is equal to y1, so these two parts cancel out. They divide out. And we're left with 1/2 rho v2 squared minus 1/2 rho v1 squared is equal to p1 minus p2. We know that the density of air is 1.28 kilograms per meters cubed from the book. And if we plug all of our values in that we know that we get 1/2 kilograms per meters cubed times 95.54 meters per second squared, the whole thing is squared, minus 3.82 all squared, meters per second all squared. Then we are left with 5,832.51 PA, which is the pressure units for P1 minus P2. Then there's no complex equation for this or principle for this. This is a pretty clear conversion. P1 minus P2 is equal to rho. This is the rho for mercury now. Careful with that. Rho GH. And that's the H we're trying to solve right there, trying to find. So we plug in what we know, and we get the 5,832.51 PA is equal to 13,600 kilograms per meters cubed times 9.8 meters per second squared is equal to h, or times h. And then we multiply these together, then divide this by these, and we get 0.0438 meters is equal to h, and this converts to 4.38 centimeters. Thank you.